Hello and welcome to the Apillisis What's New video for version 2025.2, a complete guide to the latest innovations and performance improvements. Let's start with the general enhancements. Starting from ANSA, a new deck for the Apillisis solver is now available. It will include Apillisis-specific keywords and parameters, improving the usage of the current solver capabilities. This means a more streamlined workflow and reduced setup ambiguity that fully reflects Apillisis' intended functionality. In the previous version, we introduced a significant enhancement for exporting results in HDF5 format through the new HDF5out command. This command provides control over precision, allowing both single and double precision, along with multiple compression options and the ability to write additional data blocks. In this exhaust system example, the full OP2 file containing the 40 eigenmodes was approximately 1.2 gigabytes. Requesting the same output in HDF5 with the HDF5out command, the enhanced compression mechanism was activated, reducing the file size to about 490 megabytes, offering substantial storage and I/O benefits. Building on this foundation, the new version further extends HDF5out capabilities by enabling the export of BHH, KHH, and MHH matrices and the option to write rotational components for vector results directly into the HDF5 output. In this release, we've also introduced several improvements to the block lengths method. These enhancements help reduce hard disk traffic as well as the overall disk space required during processing. Additionally, in certain scenarios, the solver can now avoid unnecessary extra shifts, which leads to noticeably faster solution times. A correction has been implemented in the frequency response workflow when preload effects are involved. In these cases, the analysis includes FSI coupling between the tire structure and the internal air pressure. Structural damping can be defined either through the global G parameter or through the material field GE. Previously, these two damping inputs produced slightly different frequency response results due to an inconsistency in how damping was applied under preload. This issue has now been fully resolved. Starting with this version, both damping definitions yield consistent and correct results, ensuring reliable frequency response behavior regardless of the chosen damping input method. Moving on to the contacts. In this version, the penetration checking algorithm for contact analysis has been fully redesigned, delivering several significant improvements over the previous implementation. The algorithm responsible for detecting potential penetrations after each Newton-Raphson iteration has been replaced with a more accurate and robust approach, particularly beneficial for complex client models. We've also introduced multi-threaded parallelization and a series of performance optimizations across the entire contact detection workflow, which help reduce computation time and improve scalability. Additionally, the handling of separation conditions has been refined, resulting in fewer Newton-Raphson iterations and a more stable convergence behavior. Finally, the accuracy and efficiency of double-order contact searches between two bodies have also been enhanced, further improving reliability in assemblies with intricate contact interactions. Regarding the optimization, a major improvement in memory usage has been implemented for topology optimization, particularly in cases where minimum member size constraints are applied. This gain is achieved for the sensitivity filtering process. Memory requirements were reduced by more than 65%, allowing larger and more complex models to be handled more efficiently. A substantial performance improvement has also been achieved for the TV max constraint in topology optimization. Previously, when a maximum member size constraint was applied on models with a large number of elements, the constraint would become overloaded, causing significant delays in the optimization cycle. This bottleneck has now been fully resolved. With the updated implementation, the TV max constraint executes dramatically faster, eliminating the excessive overhead observed in large-scale models. In the specific example shown here, the total computation time for this step has been reduced by more than 95%, resulting in a much more efficient and predictable optimization workflow. A third major improvement in topology optimization relates to the handling of stress constraints. This example involves a bracket model with 4 static subcases, a setup where applying stress constraints traditionally introduced a significant computational burden. Previously, calculating the stress sensitivities for this model added roughly 5 minutes per optimization cycle, creating a substantial slowdown in larger topology studies. With the latest enhancements, this overhead has been dramatically reduced. The same stress sensitivity calculations now require only about 30 seconds per cycle, delivering a major speedup and making stress-constrained topology optimization far more practical and efficient for everyday analyst workflows. With these updates, Epilysys 2025.2 provides more efficient workflows through extra calculation requests, improved solver speed, data handling, and optimization capabilities.